Alright, so composition. Of the first solid to solidify. So or first liquid to solidify, like a first liquid. First liquid. So CS equals to CS divided by CL times CL. So this is a very straightforward, right? Just if you cross out CS equals to CS, right? And we know that K equals to CS divided by CL. Then so get this number inside. So that will be KCL. But initially, CL equals to CL. Right? So initially, we know that CL equals to C naught. Why? Well, the reason is because if you look at the previous slide, on the liquidless slide, when we designate that stop to go there. So if you look at the previous slide, at that point, CL initially is equals to C naught. So if we organize this, so CS equals to K C naught. Right, so now we've proven that. Because we know CL equals to C, right? So something you can practice. Okay? Well, so I'm gonna go ahead and then move on. So another stuff I want to talk about is how the gradient of composition change when the ball is being solidified, or when the ball is being taken out from the liquid and solidifies the ball. Right? There must be some gradient change, as I explained. If you look at the face diagram, right? Because it's an L. So determining the composition change as the ball solidifies. So we're going to talk about this physics, but before we talk about the physics, there's a few assumptions that we need to establish. The first assumption so I'm sure that if you're doing a PhD for say master, maybe not that is important. Is that as a PhD student, often I ask is that there must be some assumptions that you need to do in order for things to be applied to to whatever the applications that you're doing, right? There's some assumptions. In other words, there's some hypothesis before you start using these equations or these conditions and stuff, right? So these are the assumptions, right? So the first assumption is that after solidification, there is no diffusion in solid ball. So no fit first ball. So this is important that when the ball is solidified that comes out from the liquid point, is that although at the solid front there's a temperature going on, because when you draw out there's some temperature residual that's still on the ball, right? And I explained that when there's a temperature, there's diffusivity. When there's a diffusivity, atoms start moving, and if start moving, meaning that there's things going on, you get second phases, precipitating second, and stuff, right? So again, is that once the ball is out from the liquid, there's no diffusion. Second is that any ejected solute mixes completely with remaining. So another assumption is that when you taken out the solid rock from the liquid, right, whatever the contaminant that's being thrown into the liquid solutions, it's fully mixed. Okay, so whatever the remaining residual that goes back into a liquid form, the liquid solution is fully mixed, right? So it's also important because you also would say that, hey, under the first assumption, when there's diffusion, there's no diffusion, right? So meaning that the atoms, there's no moving atoms, right? It's just stick there. But on the liquid front is when it's ejected, we assume that's fully homogeneous, all right? So that's an important assumption as well. Okay? So if you review the lectures on solidify, this is, when we're talking about this, it's just a more easier to understand, to draw the concentration gradient. But later on actually, we do suppose that on the liquid front, there's a concentration gradient going on. All right, so this is just, I want to let you know. So, go ahead and copy this down, and again, these are the same notes from the lectures. So if you already done writing, is that you can look at your electronic tablet and then quickly move on to the next slide. What you see is a evolutions, three evolutions, up at the middle and the bottom, and the axis. All three figures that I showed you on the axis is the distance from between the solid and liquid interfaces, and the y-axis is the composition gradient. So the composition gradients, at this point, I mean the couple and the lunar. All right. All right. Okay, so I'm gonna go ahead and move on, all right? So now, if you look at this, 1, 2, and 3. So it's evolution of the composition distribution during simplification. So the y-axis over here, each of these y-axes is Cx, the composition gradient. And the axis over here is just the distance. So the y or the x, that's fine, so it's xy. So important few things you need to take note is this line over here, this line over here, this is the tie line. Alright, so if you wanna try to correlate this with your phase diagram, this line over here is the tie line. I think this figure that I'm showing you, the only differences between the phase diagram is that this figure that I'm showing is presenting with additional distance, right? In the phase diagram, there's only the temperatures and the composition, right? So the temperature normally for the phase diagram is the y, and the axis is the gradient. But over here, if we already know a fixed composition gradient, all we have to do is look at the composition gradient change with the axis as a distance. But what it does is that you can see over here, this is the solid form, right? And then I'm using, this is the liquid, right? So the more solid that you taken out of, the more ejected element is thrown or ejected into the liquid, all right? So again, this is due because of mass conservation. So if you don't really understand what I'm actually talking about is, over here, this area, that's the solid area, should be equivalent amount the area on the liquid. Again, that due because of mass conservation. So again, this area, or whatever the element of the composition, should be also equal to this. So eventually, you have a full solid, right? This is supposed to be equivalent, right? So eventually, you have all the impurity on one end. So this is what we so-call a silicon zone refinery. Okay? Okay. Okay, so this slide is the same as what I just talked about. So you have a solid rejected from the solidification from mixed completely. So this is the same thing. I'm going to go inside. There is some empirical equation that describe this. So this is the Shah equation. So this is the Shah equation. I don't know if the book talk about this equation. So this is the Shah equation. And what it does is that this equation only explains the evolutions from here to over here, okay? So it's like a exponential increase of for describing. So it's a somewhat an empirical equation, right? So it doesn't describe this area. So I'm gonna put a double three axes. So it only describe from beginning to the end, right? So shot. And Fs is the value fraction solidified. So this is just a equation for describing the change, the evolution change of the composition gradient. So here you have k closer to 1, and then very small to 1. So K closer to 1, meaning that's a segregation is no segregation gonna happen, right? And then smaller to 1, meaning that you have more segregations, meaning that more contaminant can be trapped at the end of the rod. Right? So closer to 1, meaning that they remain homogenized. The impurity, it's difficult to separate it out. Okay? So today, if you want to have a purely metal, right? If you want to have a pure metal, right? You look at the segregation coefficient, right? If it's closer to 1, meaning that it's on fire. Okay? Okay. So I will move on. So here is, I'm going to give you a few examples. So again, solutes meaning the stuff we're going to put inside the matrix, the main material, right? So for example, dopant. Okay, so here germanium is 17, so it's higher than 1. So what does that mean? Is that this means it's a segregate in the solid then the taper, right? So K equals to 1 means no segregation. Okay. So make sure the reason why I'm copying this down is that make sure you know how you get K, right? And what does K mean? All right. Second, the second stuff is that when I say 17 over here, I say separate in the solid and liquid. So what does it like in a phase diagram that is supposed to be presented? Right, so I believe in the previous lectures, I actually draw a phase diagram that result having you calculate a K higher than 1. So try to have an idea what that phase diagram. So actually, I draw it down, but I'm not going to draw that. So make sure you review that. You know, how do you get a 17 and a K? Okay. So mostly, if everything, when you calculate K, you should have, you know, numbers smaller than 10. Okay, so I'm going to move on. Right, so another section I want to talk about is dendrite. So implications for real casting. So when you do cast, you'll get microsection segregation. Micro segregation. So AKA. Coring. So it's in homogenized. Distribution of alloy element. So what does that mean in a homogenized distribution of alloy element? So again, is when you're cooling it down, depending on the speed, right? Normally, if you look at the phase diagram, it's under the assumption that it's an optimal system. But normally, the real implication is that you will always have coring phenomenon. So it's a non equilibrium diagram. So what does that mean? I think, well, you should probably go ahead and then go back and review the word of what does that mean when I say non-equilibrium diagram, okay? Second is that dendrite or dendritic. Dendrite, 的树是这种 dendrite growth, which WHICH So also spend some time to understand how dendrite is formed. How does it form? What is the driving force for dendrite to form? Right. So when we talk about dendrite, this must be coarse dendrite or fine dendrite. Right? How do we inhibit dendrite from growing? Right. So I talked about also to deal with the cooling. The undercooling, for example, right? So undercooling will affect how dendrite will form. Is it faster or slower? Right? The second is, how about your mode? Is it a more conductive mode or more insulation mode? That will also affect the growth of dendrite, right? So these are two important phenomena that affect dendrite. And when we look at dendrite, how do we define dendrite's the width or the length? Like how do we know that? Right? So these are things. So be familiar with the concept of dendrite. Okay. So if you look on the next page, this is the dendritic growth of snow plant. the dendritic growth of a snowflake, you see that in any alloy as well. And freezing range at solidification or porosity, you know, how the evolution is kind of perceived, right? So this is also AKA what I talk about, how microporosity is being formed, right? So if you have dendrite, you have microporosity, right? Because these dendrites, they're already solid, and then the point that they kind of overstack between each others that inhibit, or inhibit at least for the liquid to fill the remaining porosities. This is the reason why we have microporosities being established, right? So moving forward is chapter 5 in the book, or chapter 6? I think it's chapter 5. I wasn't able to talk about diffusionless transformation, but diffusion transformation. So precipitation transforming is, according to the book, is diffusion transformation, right? So diffusion transformations, what that mean is that you have atoms that move, right? When you have atoms that move, you will form phases, and you have phases, you can either have precipitates or all these stuff happening. So precipitation strengthening, you can see on the bottom, you keep seeing that over here, or maybe in your final exams, you have precipitate either on the matrix or on the boundary, right? So what precipitate do, go and read the book. I'm sure that you already know that. It's an interaction between dislocation and precipitate. So if you have more precipitate, what does that do to material strength? Does it increases or decreases? Does it increase its ductility or decrease its ductility? So you might want to have a good reason to explain what does the dislocations and precipitates play in a role of the final material properties. Okay? Okay. So here's again, I believe just last week I touched upon the topic is that you can see as the precipitate particle grows with time, their interfaces with the matrix transitions from coherent to incoherent. So you want to write that down. So the matrix transfer from coherent to incoherent, resulting in a drop in yield stress. So the important thing is that when you see a precipitate, particularly at that interface, that's where when you have incoherent interface that's being developed. But the most important thing that you must at least start with a solid solution strengthening, right? Solid solutions meaning that, as I always keep using as an example, salt or sugar, right? When you put into water, you have enough of, content is just one solution, right? So that's a solid solution strength. Now, if you add more salt and sugar, eventually you have an incoherent, second phase is incoherent interfaces, right? So over here, you can see at the beginning you have solid solutions, and then aging with time. So aging meaning that you're just holding on that temperature and time, right? That temperature can be room temperatures or temperature that can be, 1,000 Celsius, depending on. And then eventually you'll get a range of a correlative dispersion of coherence and coherence. So you will have a phase, like you have these precipitate either on the boundaries or on the matrix. That's fine, right? And then at the third state, so it's 1, 2, 3, and the final state you'll get like incoherent, a chunk of big incoherent. So these are like large precipitates and stuff. Right? So that will result in the drop of yield stress. All right. So if you look on the next slide, so this is stage 1, 2. So I draw stage 1, 2, 3. Okay. So if you move on to your previous slide, so stage 1, 2, 3 is over here, 1, 2, 3. Okay, so just put 1, 2, 3, 1, 2, 3. This is like the 1, 2, 3. Okay, so you have on the left hand solid solution. strengthening, and then you have, so when you have precipitate, there's a phase evolutions that's being established. Okay? So it starts with a theta blah blah. So that's a semi-coherent interfaces, and then eventually you have a theta particle that's being used. Now there's a name for that. I'm sure last week I already talked about. This is what we call a GP zone. So these specifically are crystallographically coherent with the matrix, and their fine distribution actually increases the mechanical strength. So it's the GP zone. Okay. So that's normally you can see between the incoherent interfaces on stage two. Okay. So if you look on your second slide, so this is a better, higher resolution from TEM, the non-custom bone images. Okay. I think so I think the question last week I was talking about is, you know, how does that correlate with the phase transformation rate and the phase evolution? Because if you cool down at a certain temperatures, you get fine particles. But if you cool at a higher temperatures, you might get coarser particles as well, right? So how does that plays into it? How do we control this microstructure? So that's the main. But the reason why I'm mentioning this is that I want you to be familiar with these terminologies. Okay. Okay. So move on. So other few notes I can again copy that. It's the same notes we copy, just again for diligence. So there's the steps for precipitation forming in aluminum coupled alloy. These are the steps you need to be aware of. Right? Steps during precipitate formation in aluminum coupled alloy. So this is the same in other alloys as well. So I'm just again trying to be consistent with all the other stuff. So first, during aging, particle form grow, right? So your first form a GP zone, right? And if you have the notes from last week, is I explained you have coherent, incoherent phases going on, right? So that's the first. Now the second is that you form a GP zone, grows larger, right? LARG. And referred to as theta blah blah particles. Right, so theta blah. And the final third is that you have larger theta particle. Face are coherent. Edges are incoherent. Right? And then final step 4 is larger theta particles. Both faces and edges are incoherent. Okay, so first you form a GP zone. You have a GP zone that turns into theta. you have log bar, but phase are coherent, edge are incoherent, and then finally you get large theta particles. That's the precipitates. And both phase and edge are incoherent, right? So, 4 stages. So you got theta, you got GP, theta blah blah, theta plot, and then theta. Alright, and then theta plot. The phase are coherent, edge are incoherent. Theta for both phase and edges are incoherent. Right. So these are the same notes that I copied last. All have the rate, the 310 or 310 rate. 310, okay. All right, so I'm gonna move on. All right, these notes, I'm gonna, for these notes, you don't worry, I'm gonna upload it by end of today. And again, these are the last week's stuff, okay? So this is, I'm gonna cover very quickly, and again, the same thing is the fraction of the fraction of reaction, right? What's the precipitation in terms of time, right? So say this is 1 that you have from 0 to 1. 1 is fully transformed to a theta particles, right? So you will have exponential decrease eventually like that. So this is log time, and over here is basically the theta particles. Right? And then you can, this is pretty straightforward, this is the GP zone, right? Now, the thing is, during these times right now, it's not really clear the transitions, like how does it transitions from GP blah blah to blah blah and then blah and then, right? So exactly at what time stage, right? But we do know it definitely starts with GP and then eventually have a precipitate, right? That's the thing. Okay. So over here is for each curve we begin in the single phase alpha region. So if you cool rapidly to a temperature in the two phase regions, 450, 300. It's not, so if you just look at this directly, there's really no proportion that's going on. Right? Now. Yeah, so over here is, you can see that if we take, if we look at the TTD diagram for 350, for 450, 400, and 350s, particularly at 350 and 450s, the precipitates of these, they're completely very different, right? And I'll explain that a little bit more. But if you look at the log time scale, which one is faster? 400 Celsius, right? And then 450 and 350 is moderately slower compared at 400, sorry. Another stuff I want to, kind of bring out is in the industrial scale application. Normally, if you want to precipitate, you cool down to room temperature and then you raise it to the desired temperature. Right? So this is, again, the same slide, last week. You cool down and then raise to a dozen of temperatures and you sit on that temperatures and allow it to precipitate, right? And then, now when you precipitate and you talk associated with time, that's aging, okay? Now, aging's, it can be good, but it can be bad, right? So if it's bad, it's overaging, right? Because if you have overaging, meaning that you have a second phase that is too much, that it be destructive on your final material strength, right? So if you sit there long enough, it's aging. That's a phenomenon called aging, but you want to control the time so that it doesn't overage, okay? So again, few notes I want to talk about. So practical process to make fine precipitates. So one, you have a solutions, heat treated to form a single phase solid solution. And then you cool rapidly, right? So that's quench. Room temperature. Or below. And then what you do is you again reheat. Corresponding to the lower half of the heat vector. Right? So, in terms of the precipitate, there's two things that's kind of pulling the string, if that's the right terminology. One is the diffusion, right? Because when you cool down, there's a temperature change, atoms diffusion. The second, because we're cooling down, there's a temperature, there's the kinetic energy that we also have to consider, right? The thermodynamic, right? So as I kind of, when you copy this down, you have to think about these two strings as pulling, right? So if you have a higher temperatures, the atoms like to vibrate, move around. They're more energetic, motivated, so they move around, right? They move and form, right? So it's a lot easier when you already nucleize. If you have a nucleize, right? It starts growing dramatically, fast, right? Because the temperature is hot, you get motivated. So if you have a nucleus that forms, it will grow. The precipitate will grow. Another thing is when I mentioned about the thermodynamics part, like that part, that stuff is that's what we call the undercooling. So when we undercooling a lot, that actually helps. If it's a liquid, it wants to solidify, right? You start forming a lot of nuclei, right? So if you start forming that nuclei, But if your temperature is too low, it's hard for the nuclei to grow even larger. So now on the next slide is these two things is sort of pulling the string is like, okay, do you want to have it precipitate closer or finer, right? So this is the balance. And if you look on the previous slide, you will see the TTT diagram. There's the nose curve, right? So at what places do you want closer or finer, okay? And that's already, it all comes down to your applications, right? Okay, so I'm gonna move on. So this slide is what I was trying to talk about is you have 350 produce a finer microstructure than 450. Why is this? So there's two strings that's pulling. One is the driving force, that's the diffusion, and one is the kinetic, right? So the kinetic is also doing that part of the job. So at 350s you have a rapid nucleations and sluggish growth, right? So 350s, when you start cooling the undercooling, right, that energy help us to form these small nuclei in the solution, right? But the growth is slow because it's a lower temperature compared to 450. So at 450 you have a sluggish nucleation and rapid growth. So these are important. Right? And again, the cutoff is key cutoff, right? Okay? All right, let's have a break and then we'll come back with our final session.